When we first encounter derivatives, the most basic rule to follow is if we start with f of x equals x to the power of n, then f prime of x, the derivative, equals the power that used to be there out front as a coefficient, n, x to now the new exponent is n minus 1. Really everything that we're doing here is applications of this rule with more rules added on, and we'll get more and more rules as this unit goes on until we have way too many rules. The first one's a little trickier than it looks. If I understand that any time a variable is not listed, it's like having that variable to the same power. So just having -3 is like having a -3x to the 0, then the same rule really does apply. The 0 comes out front. 0 times anything is 0. It doesn't matter that the exponent goes to x to the -1 because the whole term goes to 0. The derivative of any constant is 0. When I go to do part B, x to the 6th, that's very straightforward. I just follow this along. The current exponent is 6, so I bring the 6 out front. I leave the variable the same. The new exponent on the variable is what used to be there, -1. So if it used to be 6 and we're subtracting 1, it's now 5. The root of x, I need to be able to portray as x being raised to some power to use my basic power rule for derivatives. I can do that. Really, this is an understood second root, first power. I can represent any variable under a root as x to the fractional power over root. So the root of x can really be written as x to the power of 1/2. If I now use my rule that 1/2 comes down, x has a new power, which is 1/2 minus 1. That means I really get the 1/2 coefficient out front, x to the -1/2. I'm not allowed to have a negative or fractional exponent in my final answer, so I'm going to bring it to the bottom of the fraction. What's left over on top is this 1. On bottom is the 2 that was already there, and then an x to the +1/2, which I really can write as 1 over 2, the square root of x. So a lot of steps here to get from my original root of x to my final answer, 1 over 2 root x, but it comes up often enough that you should probably have it in your notes and kind of see this process and how it ends up with something like that. For f of x equals 1 over x to the 3rd, in order to use our power rule, we have to rewrite this as x to a specific power, in this case, the -3rd. So we bring it up to the top as x to the -3rd. Once we have it there, we apply the power rule. We bring down the current exponent, -3, put it out front, leave the variable with its original exponent, -1. The key here is that -1 makes it a -4, not a -2. When first doing these problems, that's the common mistake that students make. They think it always lowers by 1, this 6 went to 5, so a 3 should go to 2. It's not that it lowers by 1 in absolute value, it's that it goes 1 more negative. So a negative exponent gets even more negative from this process. This really gives me -3x to the power of -4, which means the -3 can stay on top. To the bottom goes x, now to the power of +4. For sine x, it's just one you have to have memorized or have in your notes. Basically, the derivative of sine is cosine. The derivative of cosine is negative sine. So here, I just have to write cosine x. For using the rules of differentiation to find the derivative of the equation, each of these f of t's, we're asked to find f prime of t. We basically need to treat each term separately and see what occurs with that term. So the first term, 3t squared, the 2 comes down, gets multiplied by the 3, and gives me 6t to the 2 minus 1, which is just the first power. Here, when I do 7t to the first, the 1 comes down. 1 times 7 is just 7. And then t to the 1 minus 1 is t to the 0, or means the t drops out. When I take the derivative of a constant, it always equals 0. So I really have 6t to the first plus 7, which I can write as 6t plus 7. For part B, we start with 4t to the 5th power. The 5 can come down. 5 times 4 gives me 20. T used to be to the 5th power. I'm going to subtract 1 from that, and it becomes t to the 4th power. I have just t to the 1st. The 1 comes down times the 1 that's already there and gives me a 1. 1 minus 1 gives me 0, so the t drops out. I just have the number 1 here. Finally, this negative 8 over t, I should say, is really negative 8t to the negative 1. The negative 1 comes down, so there used to be a negative 8 here. It's multiplied by a negative 1, and then the power on t becomes negative 1 minus 1, which is negative 2. So I can write this as 20 t to the 4th plus 1. Negative 8 times a negative 1 gives me positive 8, so it's a plus. The 8 is on top, but when I take this t to the negative 2nd to the bottom to make it a positive exponent, it becomes 8 over t to the 2nd. Here we're asked to first take an original function, then rewrite it in a form that we can differentiate before differentiating it and simplifying it back to an original version. So here the way we're going to rewrite 5 over 3x to the 7th is as y equals 5/3 times x to the negative 7. When we differentiate, that negative 7 gets multiplied by this 5 to give me y prime equals negative 35 still over 3 x to the negative 7 minus 1, which is negative 8. To then simplify it in a way that is mathematically correct, we want to take any negative exponents, move them to the bottom as positive. So the negative 35 is left alone on top. On bottom, we have 3x to the positive 8th. When we have a root, again, we want to rewrite it as a fractional exponent, where this becomes y equals x to the power, which is underneath. That's 3 and is the numerator. The root number is 5 and it's the denominator. We're now going to bring down that fraction. So y prime, bring down the exponent. The 3/5 goes out front. The x stays, and it becomes 3/5 minus 1, which is really minus 5/5. That means that I get 3/5 x to the negative 2/5. When I simplify, y prime then becomes the 3 that stays on top, the 5 that stays on bottom, and now when I go to make this positive on bottom, the bottom of the fraction, the denominator, the 5th is the root number, so it's 5th root. The top of the fraction is the power, still x, now to the 2nd power. So I started out as just the 5th root of x cubed. I ended up with 3 over 5, the 5th root of x squared. When I'm asked to find the slope of the graph of the function at the given point, basically I'm taking the x value, plugging it into the derivative, and solving to find that slope. So when I take the derivative of this f of x, f prime of x, the 2 comes down, times 2 gives me 4x. 2 minus 1 is just first power understood. The negative 9, take a derivative of a constant, it becomes 0. So I'm just left with 4x. When I put negative 3 in where I see an x, it becomes 4 times negative 3, telling me that the slope is negative 12 at that point. For b, I can't do a derivative yet. We will be able to do a derivative for something like this using what's called the chain rule in a couple classes, but for now, I need to square everything out before I can use the rules that I know how to use for derivatives. So I'm going to do 5x minus 1 times 5x minus 1. 5x times 5x gives me 25x squared. 5x times negative 1 gives me negative 5x. 5x times negative 1 gives me negative 5x. When I combine those, I get negative 10x. Negative 1 times negative 1 gives me positive 1. So this is my original f of x equation. When I go to take the derivative, f prime of x, 2 times 25 gives me 50. X goes from the second power to just the first power. 1 times negative 10 stays negative 10. X goes from the first power to the 0th power. In other words, it drops out of the problem. This plus 1 is a constant, so when I take the derivative of it, it goes to 0 or drops out of the problem. And now I'm going to plug in a 0. Everywhere where I see an x, it becomes 50 times 0 minus 10, which is just negative 10. So at an x value of 0, this equation has a slope of negative 10. Consider the given function and point. Find the equation of the tangent line at that point. So first thing I'm going to do is take a derivative. This is going to help me find the slope of the tangent line. 5 times 3 gives me 15. X used to be to the 5th. It's now to the 4th. 3 times negative 7 gives me negative 21. X used to be to the 3rd. It's now to the 2nd. 1 times a positive 10 gives me positive 10. X used to be the 1st. Now drops out of the problem. And negative 2 is a constant, so it drops out of the problem. This allows me to find the slope at this specific point when x equals 0 by plugging in 0 everywhere where I see an x, which leaves me with an answer of 10. So we now know that the slope is 10. We know that this point is on the line. Because it's the intercept, it makes it easy, and I could jump right to a y equals line and say that the equation of the tangent line is y equals 10x minus 2. But just to show how I would get there if I didn't have a point that had 0, basically I'd want to write y minus the y coordinate, in this case y minus a negative 2, equals the slope times x minus the x coordinate, which in this case is 0. When I do this out, y minus a negative 2 becomes y plus 2 equals 10 times x is 10x. 10 times 0 is 0. Subtract 2 from each side, and I do get y equals 10x minus 2. This is my final equation of the tangent line. Again, if I didn't have 0 as my x value they were giving me in the point, this math would definitely be more important because this 10 times this number would come together to make a very different intercept.